Good morning, everybody. My name is Ilerioluwa Giwa, and I'm a PhD student in the Department of Construction Management at LSU. Today, I'll be sharing our collaborative project titled Dual Reinforcement Approach for Printable Cementitious Materials, looking at the structural properties of the 3D printed element. So in agreement with previous presenters, concrete 3D printing offers a lot of benefits. With the goal is to print more efficiently and more faster. As such, this additive construction technology offers a platform technology that can be used for several applications. However, there are some factors that currently hinders the widespread adoption of this construction technology, such as presenters discussed earlier, how do we design our 3D printed buildings and structures to code, and also the issue of how to ensure high process reliability and high process fidelity during the construction 3D printing process. And more related to our research is the issue of automated reinforcement. Concrete, which is the widely used printing material, is brittle, which kind of limits its structural applications. So while there have been several solutions that have been proposed, it is important that these solutions are seamless and also compatible with the material deposition process. And also your 3D printed element should be able to maintain its structural integrity. And while other benefits are claimed by this construction technology, is not compromised. So in the existing literature, there are several reinforcement integration approach which covers several processes, sequencing, different levels of complexity, and also different types of reinforcement materials. Just broadly, your reinforcement can be integrated before the deposition process or during the deposition process in the place of when you have an inline or maybe a simultaneous integration of the reinforcement while 3D printing. And for sure, you can also integrate your reinforcement after the 3D printing process has been completed. So the penetrative technique is one of the most attractive reinforcement integration technique because it has the potential for full automation, and also you can provide some kind of interlayer reinforcement to your 3D printed element. Several studies have shown how using short discrete reinforcement such as your nails, staples, and screws can significantly improve your mechanical properties of your 3D printed elements. So in our study, we have employed the use of a dual reinforcement technique where we have 3D printed our 3D printed structure with a fiber reinforced material. In this case, we have used brass coated steel fibers, 13 millimeters length, at a very high fiber dosage at 2.5% volume. And because we know that fibers do not provide any kind of interlayer reinforcement, we additionally were further strengthened the 3D printed structure by integrating short threaded vertical reinforcement in a semi-automated process. So as the printing material used in this study, we have tapped into the findings from the first part of this project, where we have evaluated how different mixture design strategies can actually impact your printability and also your mechanical properties. And the key finding was that at very high dosages of fiber, we were able to significantly increase the flexural strength and also the tensile properties by up to 129% and 149% respectively. I should also mention that in this study, we have only tested small prismatic beams of dimensions 40 by 40 by 160 millimeters beam. So as such, we selected the best performing material and have used it for printing in this case. So the main objective was to look at both the fresh state properties and also the mechanical state properties. And for the mechanical state properties, we have actually evaluated much bigger prismatic specimen, in this case 100 by 100 by 350 millimeters. So we have tested this specimen in a 4-point bending test, considering the different loading directions to evaluate the anisotropic properties of these 3D printed beams. So as such, we printed 4-layer sample, which was tested in the X direction and also in the Y direction. X direction, where the load was applied normal to the XY plane, and Y direction, where the load was applied normal to the XZ plane. And then finally, for the Z direction specimen, we've printed a 14-layer specimen at a maximum interlayer time gap of 3 minutes, and then tested in the Z direction. So to evaluate the effectiveness of the additional threaded reinforcement insertion process to this, how it affects the structural properties, we have developed an electromechanical system which was adapted to our 3D printing system to seamlessly integrate the short reinforcement into the 3D printed specimen in line during the printing process. And then using some design considerations from ASCI 318, we have adopted 3 threaded reinforcement for each printed beams, and strategically positioned it towards the tensile region of the printed element, so it doesn't just offer the interlayer adhesion strength, but also improves, offers some kind of tensile properties. And then we tested this also in the Z direction as well. So in terms of our result for the fresh state properties, we actually evaluated the shape stability of these 2 different materials, the plain and also the fiber reinforced material. And how we've done this is we've printed 3 successive layers and then measured the plastic deformation on the bottom layer as an indication of how shape stable the material was. And then we have also evaluated the effect of different nozzle sizes on the deformation as well. So in this case, our result shows that the fiber reinforced mixtures generally had higher plastic deformation on the bottom layer, and this is of course due to the differences in the flow properties. The material with the high dosages of fiber reinforcement requires a lot more addition of superplasticizers, to be able to accommodate printing at such high dosage of material. So by this, the rheological properties have, obviously degraded, which has, led to more deformation in the bottom layer. And also we showed the effect of the shape, the aspect ratio of the printing nozzle as well. Our result shows that generally the printing with an higher aspect ratio led to generally lower plastic deformation. And then in terms of the flexural strength, we tested both the mold cast and also the 3D printed specimen in different loading directions. And our result shows that in the case of the plain mixtures, the mold cast specimen actually outperformed the 3D printed specimen by up to 50%. And of course, this is due to the presence of multiple interfaces in the 3D printed specimen as opposed to the monolithic mold cast specimen. And then in converse, in the 3D printed specimen, in the fiber reinforced specimen, the 3D printed specimen actually outperformed the mold cast specimen, even with the presence of these interfaces. And this was attributed to the preferential alignment of the fibers at high dosages in the 3D printed specimen. So in both cases, we saw that by adding high volumes of steel fibers, up to 2.5%, we were able to significantly improve the strength for both the mold cast and also the 3D printed specimen. And the improvement in the 3D printed specimen, was more pronounced than in the mold cast. And again, of course, this is due to the preferential alignment of the fibers in this. So as a result, we have observed an isotropic behavior in the 3D printed beams, and of course the specimen tested in the Z direction, which is parallel to the interfaces, showed the least performance. And interestingly, we also again confirmed that even when you use very high dosage of fibers, you do not have any kind of structural contribution to the interface, right? And then by integrating our short reinforcement in between the layers, we were able to improve the flexural strength by up to 44%. And so just to present the load deflection curve for this tested specimen, for the modcast samples, of course, we see the nonlinear relationship between the stress and also the deflection. And for these, beyond the maximum stress, we see that the specimen starts to fail in a strain softening behavior. And this was also similar for the 3D printed and 3D printed specimen tested in the X and the Y direction. But of course, this shows more ductility than in the modcast specimen based on the toughness and also the strain capacity values. And then for the specimen that was 3D printed or loaded in the Z direction, we kind of had like a brittle failure. Of course, the material sharing at the interface. But with the addition of the threaded reinforcement, we were able to, even though the strength levels were not up to the X and Y direction, we saw significant improvement in the flexural stress and also some more improved ductility, as shown by the residual strength offered by the threaded reinforcement. And just to provide some information on the crack pattern, as opposed to the plain mixtures with no reinforcement, which have shown a brittle behavior, the modcast and 3D printed specimen showed flexural shear failure, while the Z direction specimen also sheared along the interface. And by adding the extra threaded reinforcement, this failure mode wasn't observed. But by closely examining, we saw that the threaded reinforcement actually, there was a bond failure between the threaded reinforcement and the fiber reinforced matrix. And then finally, we have evaluated the porosity in the 3D printed and also modcast specimen by examining the porosity around the vicinity of the threaded reinforcement. And so we did this for both the modcast and also the 3D printed specimen. In the case of the modcast specimen, we have 3D printed a mold made of ABS and then inserted the threaded reinforcement before pouring the printing material. While in the case of the 3D printed specimen, we printed 6 layers and also seamlessly integrated the threaded reinforcement in it. So we evaluated 2 different locations, one 60 millimeters at the top of the specimen, and the location 2 60 millimeters from the tip of the specimen, to see how the porosity within this element actually varies. So generally, we saw that the total unconnected porosity in the modcast specimen were generally greater than in the 3D printed specimen. And the results to the figure to your right shows a 2D profile by the depth of the integrated reinforcement. Our result shows that generally, again, the modcast specimen had higher porosity values than the 3D printed specimen. And the location 2 here showed generally lower porosity than location 1, which was, this location had more, threaded reinforcement translates through compared to location 1. So porosity generally around the location 2 was, generally lower than location 1. So to conclude my presentation, our study has shown that different flow properties of the fiber reinforced material and also different nozzle design can influence the extent of plastic deformation during your construction 3D printing process. We showed that by adding up to 2.5% of fiber, we're able to significantly improve the flexural strength and also post-crack properties of the 3D printed elements. And our result shows an isotropic behavior, of course, which was due to loading, in different direction. And in the case of the Z direction beam, we've seen that we did not see any structural improvement even by using high dosages of fiber, but by introducing the short threaded reinforcement, we were able to significantly improve the flexural strength and also the post-crack properties as well. And finally, the CT scan analysis shows that our proposed vertical reinforcement insertion technique led to a generally more lower porosity in the 3D printed specimen as opposed to the modcast specimen. So as future work, we are also still evaluating how different other parameters like the lapping length, the lapping patterns, and other reinforcement types can influence the structural performance of your 3D printed beams. So I would like to acknowledge the support of the Transportation Consortium of Southern South Central University Research Center, and also the support of the Louisiana Transportation Research Center, and of course my home department, the B.S. Turner Department of Construction Management. Thank you.